Okay, our warm-up yesterday was this: to write as many partial gas laws as you can, starting from the ideal gas relation. Gave you time to puzzle. A lot of you guys remembered some of the partial gas laws, and you remembered that you can find all of them in this ratio, right? So, for example, if n and t were constant, right, then we could ignore them. They would become part of our gas constant, and we can simply say P1 V1 equals P2 V2. In other words, Boyle's law. Once somebody got that, then you guys were pretty much off and running, and you realized that you could have, say, constant P and N, and you would get V1 over T1 equals V2 over T2, okay, which would be Charles's law. You could have constant V and N, and you could have P1 over T1 equals P2 over T2, or Gay-Lussac's law. You could have constant P and T. You could have V1 over N1 equals V2 over N2. That would be Avogadro's principle, which is important in stoichiometry. You could have constant, what haven't I tried? Oh, yeah, constant V and T. And you could have P1 over N1 equals P2 over N2. That would be Dalton's law of partial pressures. And I guess you could have constant P and V, and you would have N1 T1 equals N2 T2. Not certain exactly when we'd use this, but it would be a way of cooling something down by reducing the number of particles in the system, okay, or increasing the particles of a system and causing it to warm up. Okay, so here are the 6 versions with 2 variables, but we then realize that there's nothing that says we have to have just 2 variables. We can then say, what if we only have constant n, right? Only, right? Well, then only n drops out, and you end up with P1 V1 over T1 equals P2 V2 over T2. And you can do that 4 different ways. You can say, okay, well, maybe I have constant V only, or constant P only, right? Or I guess constant T only, right? And if we do that, constant V would give us, let's see, P over NT. So P1 over N1 T1 equals P2 over N2 T2. I don't know when you'd use this. This one is called the combined gas law, and it gets used, a fair amount, I guess. Certainly in a lot of homework problems. Not that we're going to be doing, but this year. But ones you'll probably do, I don't know, when you take AP Chemistry. This one, I can't imagine it coming up, but it would be a real relationship. If we had constant pressure only, then you would have V1 over N1 times T1 equals V2 over N2 times T2, right? And the thing of it is, again, it's not so important that these relationships exist, but that you realize that they all come from the same idea, that you can take any constant and bring it over here and make it part of your gas constant, and then the rest of them become a partial gas law. That's how these things work, right? So if I had constant T only, you'd have P1 V1 over N1 equals P2 V2 over N2. Okay, so those are the 10 possible combinations and permutations of this, right? I guess permutations of this, okay? So, great. And if you really wanted to see how they were derived, right, I mean, I'm showing you how to sort of put your finger over a variable, but let's suppose I wanted to actually derive, say, Avogadro's principle, right? Let's suppose I cared about this. Well, I would simply say that you have 2 conditions, right? You have P times V1 over N1 times T, right? And that's equal to the ideal gas constant R, and P and T are constant. So that means I can use the same pressure over here times V2 over N2 times T, and that's also equal to R. When you have variables that you want to cancel out like this, what you do is you divide. Now, the way this is done, you just say P times V1 over N1 times T, and you divide that whole thing by P times V2 over N2 times T, right? And on the right-hand side of the equation, you just have R over R. Well, R over R is the easy part. That's 1, right? Well, on this side, the P and the T divide right out, right? Or if you wanted to, you could just invert and multiply the whole thing, right? So we would get P times V1 over N1 times T times, and then we would invert this and multiply. So we'd have N2 times T over P times V2. Well, you can see that P and T cancel right out, and now we have V1 over N1 times N2 over V2 equals 1. And what I can simply do is I can bring my V2 and N2 over to the other side by multiplying both sides by V2 and dividing both sides by N2, and I get V1 over N1 equals V2 over N2. So using just dividing to the beginning and final conditions, I can always get my partial equations. So that's technically what I'm doing in all of these, right? But it's a whole lot faster to simply cover over the parts that are constant, right, and say what is remaining is our partial gas law. Okay. So there's our warm-up. Now, what we then did is we talked about R, right? R. What is it? Right. Well, it turns out, come on, you focus. I don't see why it's not focusing. Let's try that, see if that works. Come on, you. That's a little better. So what we can say is that, first of all, it's experimentally determined. And so we can say, for example, at STP, at standard temperature and pressure, this is a thing, and this is my sneaky way of bringing up two topics at once. Right, so that's 273.15 Kelvin, in other words, or 0 degrees Celsius, right, and 1 ATM, or 101.325 kPa, or 760 millimeters of mercury, right? Those are our conditions. 1 mole of gas has a volume of 22.4 liters. And that's just true. It doesn't matter what gas it is. It's just every gas works this way as long as it behaves ideally. And so we can use that relationship. We can say, okay, R is equal to PV over NT. And let's plug and chug. So we can say, okay, well, let's use atmospheres here. We can say it's equal to 1 ATM, right, times volume, 22.4 liters, right, over 1 mole times temperature, 273.15 Kelvin. Now I could use 0 Celsius, but then this would become undefined, and we would rediscover that 0 Celsius isn't really 0 at all. It's just an arbitrary number, arbitrary placement for a 0 point, whereas Kelvin actually starts at 0 motion, so we have to use Kelvin in our gas laws. If we use Celsius, we come to all sorts of problems, like having an undefined value for our gas constant. So when we divide this out, if we were to divide this, we would say, okay, 1, right, oops, times 22.4 divided by 1 and also divided by 273.15, and we would get 0.0820, right? Liters atmospheres per mole Kelvin. Now, if we actually keep our volume and moles to higher significant digits, we find that it actually more traditionally rounds to 0.0821, but let's not dwell. However, there's nothing to say I couldn't use a different pressure value, right? I could also have said R equals PV over NT and simply used 101.325 kPa. And if I did that, I would get the same idea, except I would get 8.315. And I would have different units. I would have kilopascals times liters over moles Kelvin, right? So the same idea, but different units. And why do I have these two? Well, it's convenient to actually have two of these because sometimes we use atmospheres and sometimes we use kilopascals. And so these are both in your notes. And just choose the one that works better in your problem, the one that cancels the right pressure units. The other reason to use this one sometimes is that 8.31 kilopascal liters is also 8.31 joules. And so when you're talking about energy with the work done while compressing or expanding gases, we're going to use 8.31 for that too. Or I say we, but you would if you were doing that. So these two constants are typically used when you're doing gas law problems. Okay. Well, what problems would we actually solve? Well, if you were to look at your notes, right, you would find that we have several practice problems, okay? And we will do those next. We look at the problems that were given to you in the packet. You see that we're going to start with problem 3 because that's the first calculation problem, and I wanted to get to those as my example. There's not a lot of space here, so I copied it down below. And so if we take a look down below, we see, whoops, that here is the problem. And so the first thing I want you to realize is that to solve a problem like this, the best approach that I can think of is to start to play the what do you know game, right? And figure out what pieces you actually have. Okay, so here you have milliliters, and that's volume. However, I want volume in liters. Okay, I need liters because my R value that I'm going to use for this problem is actually, it has ATM here, but I'm going to change it because I've decided I'm going to use kPa, and my R value is going to be 8.315 kilopascal liters over moles Kelvin. Okay, so you're going to choose your units depending on what R value you're going to use, more or less, right? So I need liters, Kelvin, and moles for sure. And then if I have kilopascals, I would use 8.315. And if I have atmospheres, I would use 0.0821. Since I'm given millimeters of mercury, I'm going to have to convert either way, so I don't really care. So in this case, this is volume, but I need it in liters. And so you need to remember that 0.15, that 150 milliliters is the same as 0.150 liters. Okay, right? We divide by 1,000. Then here we have 740 millimeters of mercury. Well, I want to convert to kPa, so I'm going to remember that 740 millimeters of mercury times fraction bar, cancel millimeters of mercury, get kPa equals kPa, right? So I look up standard pressures, and I find that 760 millimeters of mercury is the standard pressure in millimeters of mercury, and 0.325. Yay, old notes, is the standard pressure in kilopascals. And then I can punch it into my calculator. And I'll say 740 divided by 760 times 101.325 gives me 98.7. 98.7 kPa, so 98.7. Okay. How many moles? So moles is our question mark. I don't know how many moles, right? T is in Kelvin, and it gives me it in 22 degrees Celsius, but I need Kelvin. So I'm going to say 22 degrees Celsius plus 273.15 equals Kelvin, right? So 295.15. And there we go. Now we've played the what do you know game and become a winner. And all we need to find is moles, right? So now we're all set up to do it. We're just going to use the ideal gas law. PV equals nRT. Okay. But I never use it this way. I never do, because then I have to do a whole bunch of rearranging and it looks confusing. It's a lot of writing. So what I always do is I take the thing I'm looking for, n, and I solve it using the variables, right? Since I have n on the right, I want to get rid of RT on both sides, right? And then I get n equals PV over RT. And then I can just substitute my numbers in, and it's easier to punch into my calculator. It's already set up for me. So 98.7 kPa times 0.150 liters over R, 8.315, kilopascal liters over moles Kelvin, times 295.15 Kelvin. And now I have my whole problem set up. Now, I will tell you that when you guys punch this into your calculators, what you tend to do is forget that the calculator doesn't know that you want both of these numbers in the denominator. So when you're punching it in, it's probably easiest for you to put these guys in parentheses. That way your calculator knows that they're both underneath the fraction bar. Alternatively, you can punch it in as like 98.7 times 0.150 divided by, and you can use parentheses, 8.315 times 295.15, right? This is what I said before, just put parentheses around it. Or you can say 98.7 times 0.150 divided by 8.315 and divided by 295.15. That will, both of these will get you the same answer, and they would get, let's see, what would you get? 98.7 times 0.150 divided by 8.315 and also divided by 295.15, and we would get 0.0060. 0.0060, and one more digit, 3 moles, right, of H2 gas. Okay, so there it is. So that's the way we would solve the problem, okay? In other words, that I would find my various terms with the proper units, rearrange the ideal gas law, and then I would plug and chug. Okay, so let's see what else. Let's try a second problem, and let's make sure we can do this. So here's problem 4, the other problem we did today in class, and we do the same thing. This time I'm going to tell you that I'm going to use R equals 0.0821 liter atmospheres per mole Kelvin. And why am I going to do that? Well, 2 reasons. One, because I want to show you that you can do this problem with either R, but also I'm given atmospheres in the problem. Once I'm given atmospheres, I'm not going to convert atmospheres to Kelvin, just use the other R value. So we play the what do we know game. 0.075 moles is already written for us, so 0.0750 moles. 5 degrees Celsius, so I need to convert that to Kelvin, and that would be 278.15 Kelvin. What volume? I don't know the volume, so I'm going to put a question mark there. And I'm looking for pressure, 0.921. So we don't have to do a lot of conversion here. This one is much easier, right? We can just start plugging and chugging as soon as we rearrange our ideal gas law. So PV equals nRT, and I want V. So V must equal, well, I would divide both sides by P, right, don't you see? And I would get nRT over P. Hooray us. Now I can plug and chug, and we would get 0.075, don't forget that leading zero, moles times 0.0821 liter atmospheres per mole Kelvin times, and I've run out of room, so shame on me. Let's write this below where I have more space. .0750 moles times 0.0821 liter atmospheres per mole Kelvin times 278.15 Kelvin, all divided by 0.921. And if I do this, then I get my answer. Notice that moles will cancel out with the moles here in the denominator of this fraction. Atmospheres will cancel out with the atmospheres in the denominator, and Kelvin will cancel out here. And the only thing I will have at the end is liters. So I'm going to end up with some number of liters. I know that at the beginning. How many? 0.075 times 0.0821 times 278.15 divided by 0.921, and it's equal to 1.86. So yay us. Okay, and there you go, 1.86 liters. Now, that takes care of most of what we talked about in class. However, if we look back at the notes, I also wanted to talk about density. And density is one where you guys haven't thought about it in a while, but density is pretty easy. Density is just mass over volume. Okay? Density. It's easier to say than it is to write on with a tablet, is just mass over volume. The thing of it is that mass over volume, mass I can find using moles by multiplying it by the molar mass. So I can expand this a little bit and make it moles over volume times the molar mass. Well, moles over volume, that works out to be molar mass times N over V. Well, using the ideal gas law, N over V is just the same thing as P over RT. So molar mass times P over RT. And this turns out to be a handy relationship. For one thing, P over RT is constant a lot of the time. And so at constant temperature and pressure, right, molar mass determines density. And that actually gets us through a lot of concepts, right? Molar mass determines density. So if you're comparing two gases, like air is about 80% N2, right? And that's 28.02 grams per mole. And it's about 20% O2, and that's about 32 grams per mole. Well, if I take 80% of this and add 20% of this, I can average it out to being air is about, I can say air is about, say, 28.8 grams per mole. That's a nice approximation for air, right? Well, let's suppose we had different gases. Let's suppose I had like, I don't know, let's use noble gases, right? Noble gases. Suppose you had helium, which is 4 grams per mole, or you had, I don't know, argon, right, which is 40 grams per mole. Okay, I'm pretty sure that's right. Don't have my periodic table on me, but I'm pretty sure that those are accurate. Well, what that means is that this would be less dense than air, and it would float, which is why we use it in children's balloons. Right? But argon would be more dense than air. And as it turns out, argon is used in fire suppression systems because if you pump argon into a burning room, it falls to the floor and falls onto any surface and covers it over and replaces the oxygen so it can't burn. So argon is a particularly useful fire suppression because it's heavy and it drifts down, displacing the oxygen. If it sat at the top of the room where there wasn't anything, everything would burn underneath it, but because it falls to the bottom, it can smother a fire very effectively. So noble gases, you can see that their density, right? You wouldn't want to have a birthday party with argon balloons. That would be a little sad. The balloons would just sit on the floor. But a helium balloon makes a nice birthday party, right? Similarly, you can't fill your airship with argon; it wouldn't float. But for different things, you want floating or sinking, right? One of the ones that's the most sort of surprising is that H2O is only 18 grams per mole, right? That means that when you have water vapor in the air, right, it's displacing something that is a higher density. And so that means that moist air is less dense than dry air. So that means that dry air is denser, right, than moist air, which is kind of surprising, right? But when water moves into the area, right, when water moves overhead, it's displacing something that has a higher molar mass. And that means that when we talk about when you're watching the weather and they're saying that the atmospheric pressure is dropping, right, you're in a low pressure system, that means you have wetter air and there's the possibility for rain. And if you have dry air, or what we call a high pressure system, it means that the air over your head has a higher molar mass and it's pushing down on you harder, right? And so the weather actually uses this concept of density when it's telling you about the air around you, right? The other thing, of course, that you can see here is that as the pressure goes up, the density of a gas goes up, but as the temperature goes up, the density of a gas goes down. And that's going to be important for things like, let's add a page, right? And so we can say that density equals molar mass times P over RT. So as T goes up, density goes down, right? And that's useful if we have something, say, like a hot air balloon, right? If you're in your hot air balloon going out to see the world, right? You want to be able to heat the air in the balloon, right? So you have a little flame under here, right? And it heats the air, right? We get, and as the air heats up, right, it becomes less dense, and the balloon floats. So, right, so the whole explanation for hot air rising is because as the temperature goes up, the density goes down. Right? And that's where we stopped the class. So, yay us.